Okay, so the big news is exam 3 is Wednesday. And the topics for this, it's everything that we've done so far. We're going to get into some new stuff today that isn't going to be on the test. So the topics are everything up through conservation laws. Anybody have any questions about the test? Okay, and then remember that we do have lab this week. It's been a long time. We're out of practice, but we do have lab this week. And then next week is the last lab exam. Okay. So the nice thing is the lab activity we're doing this week is just kind of like a review. So it should get you back in the flow with things. Okay, and then before we get into new material, does anyone have any questions on homework or anything that you'd like me to go over? I'd be happy to answer any questions related to the test or whatever. Was that a hand, Nadia?
Yeah.
Okay, yeah.
Are you allowed to go over weekly assignments?
A little bit. I can give some hints and stuff, but I won't talk about it in quite as much detail, you know.
I was having trouble with number 3.
Okay, let me look it up. Okay, number 3. Okay. So this is overall pretty similar in flow to a couple of examples that I've done. I think if I'm remembering right, I think maybe one was actually a object attached to a string like this, and then another one was a loop-de-loop. And so it starts out, parts A and B are like a circular motion problem, where when you calculate the centripetal acceleration, it come up with an expression for the centripetal acceleration, and it'll let you calculate the speed. And basically you're looking for the place where that cable tension is for the slowest speed for it to get over the top. You want that cable tension to be 0. Okay, so once you've found that, then it becomes a conservation of energy problem. You know how fast it is moving at the top, and you can use conservation of mechanical energy to figure out how fast it's going at the bottom. Yeah, at the bottom. Okay, so that's sort of the flow of it. Yes?
I have a question about number 4.
Okay. Any other questions about 3? Yes?
So then when we're first doing, like, I guess the part B of that question,
Yeah.
What should the instant be for number 1 and number 2? So, like, should the instant be at when it's at the bottom or when it's at the top?
Which one you call instant 1 and instant 2?
Yeah.
Okay, that's an interesting thing about all conservation of energy problems. There's no way to tell from conservation of energy which way the system is going. So you could ask this question as, it's going this fast at the top, how fast is it going at the bottom? Or you could say it's going this fast at the bottom, how fast is it going, or like how fast does it need to be going at the bottom to get to that speed at the top. So it doesn't matter which you call instant 1 and instant 2. There's no way for it to know what order the things are happening in. It's sort of an interesting thing, actually. Like conservation of energy, that's always the case with conservation of energy. What you need is the second law of thermodynamics to determine what happens first and what happens later. We haven't talked about the second law of thermodynamics, in case you feel like maybe you were not paying attention that day. Okay. Any other questions about number 3? Number 4?
Yeah, so it's like so for the solving this one, it's like a conservation of energy for the first part.
Yep.
And then can you do conservation of energy for the whole thing, or you have to do momentum?
Yeah, for the collision itself, you have to do momentum.
Why isn't the energy part? Why couldn't you do that before out of the way?
Why couldn't you? So if you set,
Because I did them both ways and I got different answers. So.
yeah, so why doesn't it work? I guess because I can tell you why. Because energy is lost in that collision, especially the way that we do collisions. When those things stick together, energy is lost. You can imagine there's energy either lost in the two things deforming when they stick together, or there's energy lost in the thing rattling around in the latch when they latch. But either way, there's just more energy before the collision than there is after the collision.
And then for part C, it would be energy.
Yep, that's perfect. So conservation of energy to see how fast it's going down the hill, conservation of momentum for the collision, and then conservation of energy again to see how far it goes up the hill. Any other questions? Okay. Well, the next thing we're going to get into is rotational kinematics. Or a lot of times you hear this described as rigid body kinematics. So first, let's think about what a rigid body is. So for a rigid body, this is the way that it's different from a particle, like unlike particles. Rigid bodies have both length dimensions and orientations. Okay, so now we're taking the lengths of things into account. Okay, the size of things into account. And now we can make we can differentiate between like the front of an object and the back of an object, the top and the bottom. Okay, so now we can talk about like which way an object is facing. Okay, so a particle, like if we treat this stapler as a particle, we can't really say like, is it facing like this or facing like this? Everything happens just at a single location. And so we just can't even think about, that just doesn't come into the calculations at all. But if we're treating this like a rigid body, since now we are taking into account that it's this long and this high and stuff like that, we can talk about what's happening as it does this. Okay? So that's all going to be new. And there's going to be a lot of similarity. You're going to see a lot of the old equations that we used to use in circular motion. Rigid body kinematics is closely related to circular motion. So just remember these two kind of definitions of these things. So circular motion is the motion of a particle around a circular path. And rotational motion is the change in orientation of a body about a point. Okay, so here's the best demonstration I can come up with relating circular motion, like talking about the difference between these two things. And understanding this difference is really important, okay? So circular motion, if I'm in circular motion, I'm doing this, okay? The key thing is, like, if you're looking down from above, I'm a particle, like at the middle, and I'm just following this circular path, okay? If I'm in rotational motion, I'm doing this, okay? It's taking into account the fact that my body can face in different directions, and it's those changes in directions that matter, okay? So these two things are different, but how are they the same? You know, what's similar about them? What connects them? Okay, so these are different. But they're related because when a rigid body is in rotational motion, every point on that body is in circular motion around a point. Okay, so let me show you. So if you have an object, let's think of this as like a board that's rotating around like a pin or a hinge. Okay, so think of this thing as like a hinge. And let's think of that hinge as not being able to move, like that's connecting it to a wall or the floor if you're looking from above. Then different points on this body. So let's think of what happens if you track this point. So if this body is rotating this way, okay, then this point here is following a circular path like that. Okay, and if you look at a different point, that's also following a circular path like that. So whatever point you choose, it's in circular motion around that hinge, okay? And so that's why we're going to see a lot of those circular motion equations in this stuff. in order to talk about rotational motion, we have to define two things that we haven't talked about before. The first one is called angular velocity. And the second one is called angular acceleration. And so what I'm going to do now is I'm going to define these two things, and I'm going to talk about relationships between angular velocity and angular acceleration, and then the velocity and acceleration that you're used to talking about for individual points. Okay? So let me start by defining the angular velocity. Angular velocity is how quickly and in what direction an object is rotating. And we're going to give this the variable, it's the Greek letter omega, the lowercase omega. It looks like a rounded kind of W. The units for angular velocity are units of angle per time. So that sort of makes sense, right? If you're thinking about like how quickly an object's orientation is changing, you're thinking about how many angles how many degrees, say, it rotates through for per second or per minute or whatever. And the SI units are radians per second. This is the first time we've used radians in this class. We've always been using degrees. So one thing I want you to notice about this or keep in mind is you can leave your calculators in degrees for all these calculations. The only reason that you ever have to change your calculator into radians is for trigonometric functions. And we're not ever going to have to use trig functions with these like angular velocity and angular acceleration things. And so you don't need to switch it, even though we'll be talking about radians some. Angular velocity can be broken into a magnitude and a direction. The magnitude is the angle of rotation divided by the elapsed time. And for the direction, It's going to be either clockwise or counterclockwise when you're looking at things in the plane. And we're always going to call positive. So this is sort of backwards of what you would think. Like you would think, okay, clockwise and counterclockwise, which one makes sense as positive, which one makes sense as negative. You tend to think, why not use clockwise as positive? That's not how it is, unfortunately. So you just have to remember that it's backwards of that. Positive means counterclockwise. And negative means clockwise. Okay, so let's do a quick calculation. Thinking about a rigid body rotating about a fixed point. A good example of that is a propeller. So let's say that a propeller rotates clockwise with a speed of 2,000 RPM. RPM stands for rotations per minute. What's the angular velocity in radians per second? Okay, well, to figure out the magnitude of the angular velocity, it's just going to be a unit conversion problem. What we know is that one rotation, that's one full time around. How many radians is that? How many radians in a full circle? 2 pi, yep. So one rotation is 2 pi radians. And 1 minute is 60 seconds. And so you can think of this as plus or minus. We'll think about that next. 2,000 rotations per minute. If I want to go from rotations to radians, we know that one rotation is equal to 2 pi radians. And so that'll cancel those. And now we want to go from minutes to seconds. 1 minute is equal to 60 seconds. So that cancels the minutes. Now we just have to multiply all these values out, and you get plus or minus 209.44 radians per second. Now we have to think about the direction. It says that it's rotating clockwise. Is that positive or negative? Negative. And so our answer is negative 209.44 radians per second. If you know the angular velocity of a body, of a rigid body, you can use that to calculate the translational velocity, what we think of as just the regular velocity you can calculate the velocity of every point on that body. And this is a velocity vector. So you can calculate the velocity vector of every point on the body. At first, you might think, well, if a body only has one angular velocity, right? The whole body is represented by one angular velocity. So maybe that means that every point on the body has the same velocity vector. But that's not true, actually. In general, every single point will have a different velocity vector. Okay? So let's think about how that works. So if the speed, not the velocity yet, but the speed of a point on the body is capital V, then the speed of a point on the body is equal to, this is the capital letter omega, times r. And the meaning of these are, this capital omega is just the absolute value of the angular velocity. You can think of this as the angular speed because it's the velocity without information about the direction. And this r is the distance from the hinge, or the point that this body is rotating around, to the desired point. Okay, so let me do a couple example problems using this equation. So let's say that we have, again, a board just rotating around a hinge. Here's the hinge. And let's say that we want to calculate the velocity of this point. Okay. So this is the hinge. This is the point P. And if the body has an angular velocity omega of negative 10 radians per second, about the hinge, what's the velocity vector at that point P? Okay, well, let me copy this. That hinge point is fixed. Everything's just rotating around that. And every point is going to be in a circular path around that hinge. And so this point P is going to make a circle as it moves around. That looks a little more like a ellipse or something, but pretend that's a circle. Okay. it's making a circle around that hinge. That hinge is the center of this circle. Okay? And we know that from the sign of the angular velocity, is this moving clockwise or counterclockwise? Clockwise, so it's following this circular path this way. And so the first thing we can do is, just like in circular motion problems, we can figure out the direction of the velocity vector of this point. It's going to be tangent to the path in the direction of motion, so it's going to be straight down. Okay, so we already know the direction of the velocity. Now what about the magnitude? Well, we can use this equation to figure out the magnitude. The magnitude of the velocity is the speed, and the speed is equal to the absolute value of -10, so just 10, times, I forgot to write down dimensions. Let's say that these are 0.75 meters apart. Okay, so 10 times 0.75. And so we're going to get a speed of 7.5 meters per second. Since we know the direction is in the negative y, our velocity vector is 0, -7.5. Any questions about that calculation? Okay, let's do another similar one. Okay, let's say this time we have this object again is rotating. The instant that we're going to look at here, it's going to be in a vertical position. And let's say that the hinge is at the center. And let's calculate the velocity of two different points. So let's say the point A is here. And that's a distance of 0.5 meters from the hinge. And the point B is here. And that's a distance of 1 meter from the hinge. Let's say that the angular velocity this time is +5 radians per second. And we want to calculate the velocity vectors at the points A and B. Okay, so here's the board. The hinge is at the middle. Our point A is here. And our point B is here. And first I'm going to draw the circular paths that these points follow. So the point A follows a circular path like that. The hinge is always at the center of all of these circles. And the point B follows a circular path like this. Is this rotating clockwise or counterclockwise? Counter because it's positive. So we know that these points are moving in this direction around the circular path. And so then the point A, its velocity vector is tangent to its circular path in the direction of motion. So this way, that's the velocity vector at A. And B is going the exact opposite direction because it also is tangent to the path in the direction of motion. In this case, that's like this. Okay. Is that surprising that the directions of the velocities of those 2 points are opposite, or does it kind of make sense? Like, okay, imagine like a playground carousel. Have you seen those things? They don't make them anymore because they injure so many kids, but they probably are still out there some places. Okay, imagine being on one of those things and it's spinning around like this, you know? And imagine going over to this side and leaning against it. It's spinning like this. You can sort of visualize how it would try to push you off this way, right? And if it's still spinning this way, but you went to the other side, it would try to push you off that way. So it kind of makes sense if you think about it like that. Okay, so now that we have the directions, we need to come up with the magnitudes, the speeds at these points. At the point A, the speed is equal to the absolute value of 5, so 5, times the distance from the hinge to the point A, which is 0.5. And so this is 2.5 meters per second. Now, if you look at the picture of the velocity vector at A, that's in the negative x direction. So the velocity vector at A is negative 2.50. And then at the point B, the speed is the angular velocity of the body is the same for all these points. So that's still going to be 5. But now we're a distance of 1 meter from the hinge. So this point is moving at 5 meters per second. From the picture, we figured out that that direction of the velocity vector is in the positive x. So our velocity vector of that point B is 5, 0. There's always one point on these bodies where the velocity is 0. What point would that be? Yeah, right where the hinge is. The center of that circular motion, yeah. At the hinge, if you look at the equation, that r is 0 because you're at that spot. And so there's no velocity at that point. And again, if you think about those carousel things, I don't know, I bet I have a lot more experience playing on those than any of you do because our parents used to hate us in the old days. But like, if that thing's spinning around, if you were way out on the edge, it took a lot of strength to stay on. That thing was really trying hard to shoot you off, you know? But if you could make it all the way to the middle and just stand kind of straddling the middle, no matter how fast people got it going, you could just sort of comfortably stand there. Because when you're exactly at that middle point, you're not going anywhere. Okay. Obviously, like you have a little bit of width and stuff, so that's why you're sort of rotating around instead of just staying exactly at that point. But there's no velocity right at the hinge. Okay, so that's angular velocity. The other one we have to talk about is angular acceleration. Let me look at one thing here. Angular. Okay. So angular velocity, we use that Greek letter omega to represent it. Angular acceleration, this one's pretty easy to remember. We use the Greek letter alpha. It looks like an A, you know, or a goldfish. And the angular acceleration is the rate at which the angular velocity is changing. Okay, so if you have constant angular velocity, it's not changing at all, and so you have zero angular acceleration. The units for angular acceleration are angle divided by time squared. And so the SI units are radians per second squared. And then again, for the direction, if the angular acceleration is counterclockwise, it's positive. And if the angular acceleration is clockwise, it's negative. And here are two things that you're familiar with from just regular velocity and acceleration vectors. If the angular velocity and angular acceleration are in the same direction, do you think those rotations would be speeding up or slowing down? Speeding up, yep. And if the angular velocity and angular acceleration are in opposite directions, then the rotations are slowing down. Okay, the next thing we did with angular velocity, with defining angular velocity, is come up with a relationship between the angular velocity and the velocity vector of points on the body. And we're going to do the same thing here. relating angular acceleration with the tangential acceleration vector of points on the body. So if the magnitude of the tangential acceleration vector of a point is a tan, that's what we've always been calling the magnitude of the tangential acceleration, then a tan is equal to, this is a capital alpha times r, where this capital alpha is the absolute value of the angular acceleration. So you just throw away the negative sign if you have a negative sign. And r is, well, what do you think that r is going to be? It means the same as it did with angular velocity. Think of it as like standing for radius, kind of, and it's the distance from the hinge to the point that you care about. Does it make sense that we would think of that as kind of like a radius, that distance from the hinge? Yeah, because every point is in circular motion, and this r is the radius of that circle. Okay. Okay, so let's do the same thing we did before. Do an example problem where we're going to come up with tangential accelerations of different points. So this time, the body that's rotating, let's say, is a disk. Okay, so that's the body, and it's rotating about the center. And for the points that we're interested in, let's say this is the point A, and this is the point B. And for distances, we'll say that from the hinge to A is 0.1 meter, and from the hinge to B is 0.2 meters. And let's say that alpha is equal to negative 20 radians per second squared. And we want to calculate the tangential acceleration vector at the points A and B. Ah, Okay, so the point A is traveling in a circular path like this. The point B is traveling in a circular path like this. The angular acceleration is negative, so that means the angular acceleration is clockwise. So we can think of it as like this. So the point A has an angular acceleration direction this way. And the point B has a tangential acceleration vector this way. Okay, and now we just need to calculate the magnitudes of those. At the point A, the magnitude of the tangential acceleration is the absolute value of the angular acceleration, so that's 20, times the distance from the hinge to A, that's 0.1. So this is 2.0 meters per second squared. From the picture, you can see that tangential acceleration is in the positive x direction. So the tangential acceleration vector is 2.00. And then at B, the tangential acceleration is 20 again, but this time the distance from the hinge to the point is 0.2. So we get a magnitude of 4.0. And so the tangential acceleration vector, this time from the picture, you can see that's in the positive y direction. So the tangential acceleration is 0, 4.0. Yes?
How do you know what direction the tangential is? Because,
Mm-hmm.
like when it's slowing down, it goes the same as not.
Yeah, you're right. We did talk about it more often that way, but you can think about it the same way as you think about the direction of the velocity vector. You know it's tangent to the path, and it's always in the direction of the rotational acceleration. But now the next example I'm going to do, we're gonna think about it in terms of speeding up and slowing down. Computer. Okay, so let's say we have a board. And this is the hinge. And the point we care about is, let's say it's at the end. Call this P. And the distance between these points is 0.5 meter. So let's say that the angular velocity of this body is positive 10 radians per second. the angular acceleration of this body is negative 20 radians per second squared. Calculate the velocity and the acceleration vector at this point P. Okay, there's one new thing that we didn't do in the last example that we have to do here. The total acceleration is not the same as the tangential acceleration, right? The total is the tangential plus what? Centripetal. And today we haven't talked about how to calculate the centripetal, but do you see how we can do it given stuff that we have here? We know that the centripetal acceleration magnitude is v squared over r, right? From our equation that says v is equal to omega times r, we can calculate, I mean, we have to calculate that v anyways to get the velocity vector. And so then we can use it in the calculation for centripetal acceleration. Okay? So basically the way we're going to approach this is the way we approach all circular motion problems. It's just that we have sort of a new way to calculate the magnitude of the velocity and the magnitude of the tangential acceleration. Okay. Well, this P is moving in a circular path like this. It's a little off center. That hinge is supposed to be at the center of this circle, but I'm just going to leave it. The velocity, the angular velocity is positive. So is this moving clockwise or counterclockwise? Counterclockwise. So the velocity vector is like this. Now you can think, is the angular acceleration clockwise or counterclockwise?
Clockwise.
It's clockwise. And so from that, you can say the tangential acceleration has to be this way. Or you could also think of it as those have opposite signs, meaning that it's slowing down, meaning that tangential acceleration and velocity have to be opposite. And then let's draw the centripetal acceleration too. That's always towards the center. And now we have the directions of all of those things. Now we just have to calculate the magnitudes. The speed, the magnitude of the velocity vector, is equal to the absolute value of the angular velocity, that was 10, times the distance from the hinge to P. What's that distance? Yep, 0.5. And so you get 5.0 meters per second for the speed. And from that, we can say, our first vector that we're trying to find is the velocity vector. We have it drawn in the positive y direction. So this is 0, 5.0. Now let's do the centripetal next. Since we already have that speed, we just calculated that. The centripetal acceleration magnitude is v squared over r. So that's 5 squared over, it's still the same point, so that r is still going to be 0.5. And so we get a centripetal acceleration magnitude of 50 meters per second squared. From just thinking about the circular motion, we know that's in the negative x direction. So the centripetal acceleration vector is negative 50, 0. Now the last one is the tangential acceleration. The tangential acceleration magnitude is equal to the absolute value of the angular acceleration. So that's 20. Times the distance from the hinge to the point, that's 0.5. So you get 10 meters per second squared. From the picture, you can see that's in the negative y direction. So the tangential acceleration vector is 0, negative 10. Okay, we already have the velocity vector. We have the two parts of the acceleration. To get the total acceleration, we just add up the two parts of the acceleration. So that's negative 50, 0, plus 0, negative 10. And so negative 50, negative 10. Any questions about that? Okay, so I guess the last thing I want to do today is give you sort of a table of things. So I introduced a bunch of new variables today and a bunch of new concepts, but I want you to remember that they all have a lot in common with the translational, what did I say? Quantities, concepts that you already know, okay? So let's, on one side of the table, put the translational stuff. That's what you're used to. And on the other side, put the rotational stuff. That's what we're just getting into. And I'm just going to list out all the things that are kind of analogous between the two, okay? So for translational quantities, there's a velocity vector. The analogous rotational quantity is the angular velocity. For translational stuff, there is an acceleration vector. For rotational stuff, there's the angular acceleration. And actually make this a tangential acceleration. It'll make more sense with everything. Okay, so next, for translational things, if the velocity and the tangential acceleration are in the same direction, it means that the object is speeding up. And similarly, if the angular velocity and angular acceleration are in the same direction, it means the rotations are speeding up. Then for translational, if the velocity vector and the tangential acceleration vector are in opposite directions, it means the object is slowing down. And for rotational, if angular velocity and angular acceleration are in opposite directions, it means the object is slowing down. Some other stuff that's, forget about that. The last one, there's one last thing I want to get in here. We haven't gotten to this yet. This is what we're going to get to either towards the end of next class or the class after that. But the big result that we got in translational kinetics was that F net is equal to the mass times the acceleration. And we're going to see